Hello students, welcome back again. Finally we have come to the last session for this first module. This session is about the operation amplifier application circuits. We have already seen some of the applications in the previous session. Before we go there, let us see what is the outcome of this particular session that we are doing. Upon successful completion of this session, students should be able to analyze operational amplifier circuits and their applications. So far, we have been seeing the applications. We have already done the peak detector in the previous session. Plus, we have seen a comparator wherein we compared an unknown signal or an input signal with a zero voltage. That means one of the terminals was grounded, the other terminal was the input terminal. So we could always compare the input signal with the zero. So we call that circuit as a zero crossing detector. Continuing with that, we will see some more comparators this time, and then we'll move on to filters, oscillators, and a very unique application of a nonlinear amplifier. This is a circuit for a comparator again, but this time we are not comparing the input voltage with zero. This time we are comparing it with a known reference voltage which is other than zero. It could be a positive reference voltage or it could be a negative reference voltage. Let us go back and see this particular circuit. How exactly is it that we can do this? The first circuit on the left side, this is the one. We are going to compare the input signal here with what we call as the positive reference voltage. Now this positive reference voltage here VCC is applied at the inverting pin through R2 and R1. So effectively, can you tell what is the voltage we are experiencing at the inverting terminal? Exactly, this is a voltage divider circuit. So the voltage we see at the inverting pin of this amplifier is R2 divided by R1 plus R2 multiplied by the applied voltage which is plus VCC. Okay. So we are comparing the input voltage Vi with a positive reference voltage given by VCC times R2 divided by R1 plus R2. This is actually a voltage divider network. So how do you expect the circuit to behave now? Okay. So if you are going to look at the waveforms here, let us say this is the input, this is a graph that we are trying to plot. Okay. So this is a graph you are trying to plot. This would be your output voltage whenever the input voltage, like let's call it with respect to time. Okay. So let us assume that the input is a sinusoidal voltage. Okay. This is the one. So whenever the input is larger than the reference voltage, so this becomes your reference voltage Vref. What is Vref? Vref is nothing but your R2 divided by R1 plus R2 times plus VCC. So whenever this condition happens, which is happening in this region here. So in this shaded region that I am trying to show, what exactly is happening? In this entire region, your input voltage is above the reference voltage. So whenever this happens, the output saturates to plus Vsat. And whenever it does not happen, that is whenever your input is below this line called Vref, then your output becomes minus Vsat. So what am I essentially doing now? I am saying my input voltage, whenever it is larger than reference, the output is plus Vsat. Otherwise it is minus Vsat. So net then I am saying I am comparing it with a positive reference voltage, not a zero crossing detector but a V reference crossing detector. Whenever it crosses the reference, I get plus Vsat, otherwise I will get minus Vsat. Similarly, moving on, the circuit we have on the right hand side, this is the same circuit. The only difference is this time we are comparing with a reference which is a negative voltage. Okay. So what is a negative voltage now? Everything is the same. In this equation, this simply gets this plus over here, this gets replaced by minus VCC. Rest all the equation remains the same. So where is your minus reference point? The minus point could be somewhere over here. So now what is the shaded region? The shaded region becomes this entire thing, right? So whenever your input is larger than this negative voltage, my output is positive, else it is minus Vsat. Hence, we can connect any other reference at the inverting pin and get what we call as a non-inverting comparator with a reference voltage. So this is a very unique application for comparator other than a zero crossing detector. Now moving on, let us see the next application for this circuit. This again is a very interesting application. This is something which we call as a window comparator. What did the previous circuits do? They either compared with a positive reference or they compared with a negative reference. Now suppose I want to have a circuit which can tell me when is my input voltage within a known voltage window. Can I have my output during that time or not? Okay. So for that, this is a circuit that we are showing. This consists of two comparators now, because I have to compare two thresholds, right? So let me call these two thresholds as, one I will call as the lower threshold point, okay, and the other one I am going to call as a upper threshold point. If you can see the curve on this side, my x-axis has Vi, right? So whenever my Vi is in the zone lower threshold point to upper threshold point in this particular zone, right? So whenever it is in this zone, I want my output to be 0 volts, else my output will be plus Vsat. So if this is a behavior expected, let us see how this particular circuit functions. Now let us say initially the input is less than the lower threshold point. Let us say I am at this point, okay, I am at this point. At this point what happens? Okay, my input Vi is less than the threshold, lower threshold point. So in this here, the input at the non-inverting pin is larger because Vi is less than lower threshold point. So what will happen is this op amp is going to be plus Vsat, in the sense this diode would now be forward biased and it can conduct in this fashion. Now let us see whether the lower op amp comparator also turns on. In this case what is happening, the voltage at the non-inverting pin is less than upper threshold point, meaning what? It is definitely greater than, it is definitely below the upper threshold point. See here, I am on this side, okay, whereas my upper threshold point is somewhere here. So my Vi is definitely less than upper threshold point. In this case what happens? Since the input at the inverting pin is larger than the input at the non-inverting pin, the output becomes minus Vsat. The moment it is minus Vsat, this diode becomes reverse biased, right? Reverse bias means no current can flow. So what happens then? The output is plus Vsat and it flows through RL and hence establishes V0 as plus Vsat. Okay? Now let us look at the scenario when your Vi is greater than the upper threshold point. Okay, so in that case I'll again go back here. Fine. So let's go back and try to redraw. Okay, this is a scenario now wherein I want my Vi somewhere over here, right? So my Vi is greater than the upper threshold point. Let us see what becomes the values of the two comparators. Let us look at the lower comparator first. Okay. In this case, Vi is greater than upper threshold point. So what happens? The input at non-inverting pin is larger. So this output is plus Vsat and the diode conducts. If the diode conducts, the current can flow and I can have the output as Vsat, provided the other comparator is not troubling me. Let us see what happens to the other comparator on the top. In this case, Vi is greater than UTP means what? It is definitely larger than LTP. Go back to this waveform here. I am here. So my Vi is definitely greater than the lower threshold point. So what does that mean? My input at the inverting terminal is greater than the input at the non-inverting terminal. So the output is minus Vsat. So this diode is reverse biased. Once it is reverse biased, it cannot conduct. So therefore, the output is only because of the lower comparator and the D2 being on, and the output is again plus Vsat. So in both the cases we have seen, whenever the input is below the lower threshold point, the output is plus Vsat. Whenever the input is above the upper threshold point, the output is again plus Vsat. Now let us see what happens when the input is in between these two thresholds. For that, let us go back and try to redraw and see the scenario, what happens. So let us see now my input is in this region. I am trying to show a blue region now. Earlier it was less than LTP or greater than UTP. Now it is greater than LTP but less than UTP. That means it is in this band now wherein I want to check. Okay. Now let us see what happens to the upper comparator. In the upper comparator, my Vi, it is greater than lower threshold point. So the input at inverting pin is greater than the input at non-inverting pin. So therefore the upper comparator is at minus Vsat and hence diode D1 does not conduct. Let us see what happens to the lower comparator. My Vi is less than upper threshold point. Means what? The input at V plus V at non-inverting is less, or in other words I can say the input at minus pin or inverting pin is greater. See here, because UTP is greater than Vi. What happens? This comparator is also at minus Vsat, meaning what? Even this diode is not conducting. So in both the diodes are not conducting, no current flows, and then we can safely say V0 is at 0 volts. Okay. So what does that mean now? Whenever my input is entering in this window, okay, whenever my input is entering in this window between lower threshold point and upper threshold point, my output drops to 0. Thus, I can say that this circuit behaves like a window comparator. Window means what? Whenever my input is within this window of voltage, my output is 0, else it is logic 1 or plus Vsat. So this is one application where you can use two comparators and achieve what we call as a window comparator. In this case, the output was 0 whenever it was in the window. We can also have, we can rearrange these terms. We can rearrange the LTP and UTP, just put them top and bottom, and we can get an output waveform which will be something like this. Okay, that means the output will be 1 or plus Vsat whenever it is in the window, else it's otherwise. The only difference is you have to simply interchange this lower threshold point and upper threshold point, and the circuit behaves in that fashion. Now let's move on then to the next application for this, which is called as active filters. Now before I can delve into this topic, let us go back to the board and see what exactly do we mean by a filter. Now we all know op amps can be used for signal conditioning and signal processing. Now what does that mean? Any signal that you take has a certain frequency, or it can be a mix of certain frequencies. In the sense, it can be in a certain range of frequencies. Now suppose let us say I have a frequency range going from F1 to F2. Okay, if this is the graph that I am looking at, okay, this is at 0 frequency, which is typically what we call as a DC, and let us say this is where I am having F1, and let us say this is where I am having F2. Now this is typically what I want the gain, right? The gain of my op amp, and this is with respect to frequency. What does filtering mean? Filtering means my input signal can have any amount of frequencies, but if I give this particular signal to my op amp, okay, then if my op amp is acting like a filter, then you can design the filter in many ways. Okay, let us classify these filters. Now filters can be of generally 3 types. Something called as a low pass filter, which means it passes only the low frequency components. Then we have something called as the high pass filter, meaning what? It can only pass the frequencies which are beyond a certain frequency. And we have something called as band pass filters, meaning what? I can pass the frequencies only which fall in certain band. Now what that means in terms of waveform? Let us assume that this is a gain that I am looking at, a certain gain which is constant. So let me draw this by dotted line. Now suppose if I want to have a low pass filter, what does that mean? If the lower cutoff frequency is F1, then I should pass all the frequencies below f1 but block all the frequencies beyond f1. What does that mean? If I were to have a gain, it's an ideal filter, okay. So it will amplify all the signals which fall in this frequency from 0 to f1, but it will attenuate, see zero gain. Any signals which come beyond f1, it simply amplifies by gain of 0, means what? It does not pass it. So this is called as a low pass. I am only passing the low frequency. So this entire range now becomes a low pass filter, okay. Now what if it is a high pass filter? In case of a high pass filter, it is exactly the opposite. What does that mean? Let us say that particular frequency I am looking at is f2, okay. That means what? I do not want to pass any frequencies which fall below f2, but after f2 I want to pass everything. So what does that mean? Up to f2, whatever is the frequency, I don't amplify them at all or amplify by gain of 0. Beyond f2, I pass them all, means what? I amplify all those with a gain of AV, means this becomes your high pass filter. So low pass means only low frequencies are passed where higher ones are suppressed. High pass means all the lower frequencies are suppressed, only the higher frequencies are passed. Then what about the band pass? A band pass, as the name suggests, it only amplifies the signals which fall in a certain band. Just like you have a window comparator, right? What does that mean? It only passes the frequencies which are in the range f1 to f2, or the band is f2 minus f1, whereas any frequency component below f1 or above f2 it simply blocks. So this is called as a band pass filter. So this is basically the context through which we have to analyze all the filters that we are going to study now in the future. Now can these filters be achieved using simple passive components? The answer is yes. We use what we call as RC filters, but the drawback of the passive components is they do not provide any signal gain. They in fact go and attenuate that, okay? You may not get any gain there, there is attenuation there. So if you want to have a gain, you need to have an amplifier or try to put an active component into it. Typically it was done using JFETs earlier or BJTs before that, but nowadays we have such a versatile device like an op-amp, using which we can have what we call as active filters. Active filters simply mean the same filter techniques but using active device like an op-amp. So let's go back and see one of these applications as to how we can use as an active filter. The circuit shown here in the slide is that of an op-amp which uses a simple RC network R and a C in achieving what we call as either a low pass filter or a high pass filter. The circuit on the left side is what we call as a low pass filter, okay, and the circuit on the right side is your high pass filter. Now we can analyze this in a very simple way, but let's tell what the configuration is. The configuration for both these circuits is what we call as a voltage follower configuration. What does voltage follower mean? There is a unity feedback, right? The entire V0 output is connected back to the inverting pin of your op-amp. That means the gain is unity. Okay, actually I am not amplifying here. I am not amplifying, even though I said I will use active filters for amplification. But the thing I am saying here is unity gain. We will come to the filters with gain at a later stage. So these circuits, even though they are active filters, here the gain is unity, but at least there is no attenuation. So that is the starting point. Okay. Now how do you analyze this circuit now? Now this circuit is configured as a voltage follower, as I already said, in which you have the input connected at the non-inverting terminal. Okay, this is where your input is going to be connected at the non-inverting terminal, that is Vi. Okay. Now this Vi, let us say initially when the frequency components are very low, let us say we took the example 0 to f1, right, where f1 is a lower cutoff band. So till it reaches a frequency called as f1, okay, the signal can easily go into the op-amp and it gets passed through the op-amp. Why does it not go through the capacitance? The reason is very simple. What is capacitance offering? The capacitance offers what we call as a capacitive reactance. Can anyone tell the equation for the capacitive reactance? Yes? Okay, here it goes. So the capacitive reactance is given by Xc is equal to 1 upon 2 pi f, or if you want to use the word C for the capacitance, or let it be f. Okay, that means what? At lower frequencies, okay, f is what? Essentially, if it is a DC, f would be 0. At lower frequencies, the capacitive reactance of it is 1 upon 0, which is infinite, or even at lower frequencies beyond 0, it is still much larger. So, for all the low frequencies, there is no path through C, or in other words, we say capacitor blocks DC, or it blocks the low frequency component. That being the case, all the low frequency components, they are allowed to go through the op amp and then reach the output. The moment it crosses a certain frequency called as FC, which I call as a cutoff frequency. Okay. Now, what is the value of this cutoff frequency? Now, this cutoff frequency is given by 1 upon 2 pi r into C. Okay, this is the definition for a cutoff frequency FC. Okay. So, once you reach this frequency, then thereafter what? The capacitive reactance starts becoming smaller and smaller. In that case, we say the input is now bypassing the op amp and it is going through the capacitor. Once that happens, all the high frequency components get shunted to the ground rather than reaching to the op amp, and hence we can safely say that we are shutting all the high frequency components while we are allowing the low frequency. This is how a low pass filter works. In the same way, the high pass filter also works. What is it that we have to do? Simply interchange the roles of your R and C. Okay. Earlier, C was connected as a shunt, in a sense as a parallel, right? This time it is connected as a series. That means what? The input signals are offered a very high reactance for low frequencies this time. Why? It has to pass through C, only then it can reach the op amp. As we know, capacitor blocks DC. So that means what? All the low frequency components are blocked. Once the frequency exceeds the cutoff frequency, again given by the same parameter 1 upon 2 pi RC, the signal is allowed to pass through the op amp and then appear at the output. So this becomes a high pass filter. So very simple configuration, very simple techniques how to understand. Just remember the equation Xc is equal to 1 upon 2 pi Fc, and remember for DC f is 0. So if we can analyze it using this simple equation, and whether it is in series or whether it is in parallel, accordingly it becomes either a high pass filter if it is in series or as a low pass filter if it is in parallel. Now in this entire circuit that we have studied so far, the gain was unity, right? I mean, I am not amplifying. Suppose if I want to amplify, then what is it that I should do, right? So this is what I should be doing. Okay, we call them as active filters with gain. So again, this configuration here, can someone tell me what is the configuration of this op amp? I know in the previous semester or maybe in the first year of your engineering, you would have studied the basic configurations of op amp, okay, which we call as an inverting amplifier and a non-inverting amplifier. So inverting amplifier means I am connecting the input to the inverting input. Non-inverting amplifier means I am connecting the input to the non-inverting input. But in both the cases, the feedback happens at the inverting terminal. Okay, so remember that no matter whether you are inverting or non-inverting, the feedback whenever it is in a closed loop is always at the inverting terminal. So in that context, if you look at the configuration here, the first configuration on the left that we are looking at is having a feedback resistor R3 and a resistance R2, and I am applying the input Vi at the non-inverting terminal. So this becomes a non-inverting amplifier. So for the time being, if you can simply ignore that this R and C were not there, this becomes a configuration of a non-inverting amplifier wherein the gain is given by the equation. Anyone remember the equation for a non-inverting amplifier? Yes, the gain is given by 1 plus feedback resistance, which is R3, divided by the input resistance, which is R1, sorry R2. When I say input, this is I am talking about this feedback path at the inverting point. So the gain is then given by 1 plus R3 by R2, and then again whether it is a low pass or a high pass, I am having a capacitor in parallel here, means low frequencies are passed, high frequencies are bypassed or shunted down. So the circuit on the left side is that of a low pass filter with a gain of 1 plus R3 by R2. Now what is a cutoff frequency? Cutoff frequency is again given by the input devices, 1 by 2 pi R1 and C1. So this will not change. Okay. The circuit on the right side is again a similar amplifier, this time again with a gain, the same gain 1 plus R3 by R2, but the difference being I am now having the capacitor in the series to the input applied. That means what? All the low frequencies are blocked while high frequencies are allowed to go through. So this essentially becomes a high pass filter with a gain of 1 plus R3 by R2. The cutoff frequency again is given by the same expression, 1 upon 2 pi R1 and C1. So with this understanding of filters with gain, let us now try to look at a numerical or a worked example wherein we can go into much more concepts in detail. So for that, let us go back to this board and see whether we can solve one particular example which highlights all these concepts of cutoff frequency. The circuit that has been taken for this example is that of a non-inverting amplifier and an active filter, and we are going to do a high pass filter. Okay. So this a low pass filter. So this is a circuit. I am going to connect an R here and I am connect a C. So C in parallel would mean I am automatically looking at a low pass, right, because low frequencies are passed whereas high frequencies are bypassed. Now this input I am connecting to the non-inverting terminal of the op amp, means the plus terminal, okay, whereas the minus terminal I am using it for my feedback path. So what is the feedback path? I am having two resistors here, okay, which are your R3 and R2, and this is where you have your V0. Okay, so I call this as my resistor R3, this as your resistor R2, and these are your C1 and R1. Okay, so this is a very simple configuration of an active filter wherein I am using R and C and R3 and R2 for the gain part. So what will be the overall gain then? 1 plus R3 upon R2, and the cutoff frequency is given by 1 upon 2 pi R1 and C1. So in this worked example, we are giving you the values of R and the C's and ask you some very typical questions. So let us go ahead and see what the values of these resistors are. This one is given as 10 k ohm or 10 kilo ohm, and the capacitor is given as 1000 picofarad, right? So pico would be 10 raised to minus 12. The feedback and the input resistors are respectively 10k, okay, and this one is 100k over here. Okay, so the feedback resistor is 100k and the input resistor is 10k. Now the question that has been asked is, you have to find out what is the cutoff frequency. Okay, the question that is asked is, what is the cutoff frequency? So let us do the easy part first. The gain part, the question I will ask later. First let us try to find out what is the cutoff frequency. By cutoff frequency, what do you mean? Okay, so let us say this is the gain equation, gain this thing. This is a gain at low frequencies AV. It's a low pass, right? So it's having like this, and thereafter it sort of cuts off, right? That's a asymptote, which is at minus 20 decibel per decade, or it is minus 6 dB per octave. Okay, and this happens to be my cutoff frequency FC. Okay, so the expression for FC is 1 upon 2 pi R1 and C1. R1 and C1 are given by here. So it's a simple substitution problem that we start with, though we'll go into much more other issues later on. So if we simply substitute the values, this R1 is 10k and this C1 is 1000 pico. Pico is 10 raised to minus 12. We are going to get the answer as 15.915 kilohertz, right? So the cutoff frequency for this circuit with these values is 15.915 kilohertz. The interesting question comes now. Now in this problem, they are asking you to find the gain at 4FC, right? Okay, so what they are saying is, the first question was find out what is the cutoff frequency, and then they are saying find the gain at f is equal to 4 times FC, right? They are not asking the gain at DC at the low frequency, they are not asking the gain at FC, they are asking the gain at 4 times FC. To solve this, initially we have to first find what is the gain at FC. Okay? Since we are using an asymptote, we assume that it is not at 3 dB, but it is at 0, AV 0. So the gain at FC is given by which expression? The simple DC gain. So what's the DC gain equation? AV 0 is equal to 1 plus feedback resistor R3 divided by R2. Okay? So substituting the values of R3 as 100K and the value of R2 as 10K, we are going to get this DC gain as 11. It's simply 1 plus 100 upon 10, which is 1 plus 10, and it becomes 11. So the gain is 11. But typically, I would like to express this in terms of decibel. So if you want to express this value in decibel, what should I do? AV0 in decibel, okay, I have to do 20 log 11. Okay, 20 log 11. So that answer comes to 20.83 decibel. Okay, so the answer is 20.83 decibel. Now moving on, this was the easy part, right? Wherein we started by finding out what is FC, and then we said what is the value of the gain at FC. But the question they are actually asking us is what is the gain at 4 times FC. So 4 times FC means what? From FC, if I double the frequency, what do I get? 2FC, right? Now from 2FC, if I double it again, I will get how much? 4FC. So F2FC is 1 octave, remember? 6 decibels per octave means when the frequency doubles, we already seen that in the previous session. So F2FC is 1 octave, 2FC to 4FC is another octave. So we now have to find the gain at 2 octaves below FC. Okay? So for every octave, the gain falls by 6 dB. So for 2 octave, what is the fall in gain? Right. For 2 octaves, the fall in the gain is 6 into 2, which is 12 dB. When I say fall means I have to subtract. So if the gain at FC is 20.83, what is going to be the gain at 4FC? So the gain at 4FC is going to be 20.83, right, which was the gain at FC, minus 2 times this value, which is 12 dB, right? So this much is going to be your answer. So 20 minus 12, it is going to be 8.83 dB. So this is going to be the answer. Okay. So this is a very interesting example wherein if you can solve this properly, then you know this entire concept, you can actually understand what cutoff means. Don't just by heart the equations, we actually know the context and apply your concepts, right, at FC and at 4FC. It's going to fall by 2 octaves. So minus 6 dB per octave, so 12 dB per octave. So net your final answer would be 8.83 decibel. So this is how you can analyze these op-amp circuits with all the parameters that you know. Now moving on, then you can see here the next set of application that we are going to study using filters. These are essentially what we call as a relaxation oscillator. Now what is an oscillator? An oscillator is something which can generate you the waveforms. Now the waveforms can be of different types. They can be either of triangular waveforms, they can be either a square waveform. So the circuit that we are showing here is the one of a square wave generator. Okay. So this circuit here that we are showing, what does it have? Okay. Again it is having an op-amp there, again it is having a feedback path, okay, and it is having the resistors R1 and R2. Bear in mind, it is not as straightforward. So let us start analyzing it from 0. So initially, let us assume that this capacitor is totally discharged. Okay. So if the capacitor is totally discharged, that means what? I am at 0 volt at the inverting pin. So at the non-inverting pin, I will definitely be greater than 0. Okay. So that means what? The output would now be plus Vsat. Okay. So the output is plus Vsat, which I am showing here. So I will be at this point. I am at this point where the output is plus Vsat, while the input, let us say it is 0. I mean the capacitor is totally discharged, or the input at the inverting pin is 0. The moment it is plus Vsat, what happens is, now this capacitor starts to charge in this path. Once the capacitor starts charging, what happens to the voltage at the inverting pin? The voltage at the inverting pin starts going towards the positive side. It starts exponentially rising, and the time constant is given by R and C. Now let us see what is the input that we are seeing at the non-inverting terminal. At the non-inverting terminal, we have an input which is fed back from the output through a voltage divider network. So if you want to find the voltage at this point, the voltage at this point is R1 divided by R1 plus R2 times plus Vsat. Yes or no? Because output is at plus Vsat and you are applying it through a feedback network, through a resistive voltage divider network, and the voltage across inverting is nothing but the voltage across R1. So voltage across R1 is R1 divided by sum of these two, R1 and R2, multiplied by the applied voltage, which happens to be plus Vsat. So let us call this R1 and R1 plus R2 as B. Okay. So that means the voltage at the non-inverting terminal is B times plus Vsat. Now as long as this capacitor voltage while charging, it is less than this plus B Vsat, this condition remains. The moment the capacitor charges and it reaches greater than B times Vsat, okay, which we are showing here in this point. The moment the capacitor starts to charge beyond this point, now something happens at this point. The input at non-inverting is B times Vsat. Now the input at the inverting pin is going beyond that. The moment it goes beyond that, can the comparator or the op-amp not switch the output? Yes, it does, and it switches to minus Vsat. So the moment the capacitor voltage increases beyond that, the output falls to minus Vsat. The moment it is minus Vsat, what happens here? Now this from plus it becomes minus. So what happens to the capacitor now? The capacitor which was charging earlier, now it starts to discharge. Right? Remember, 0 volts, even the capacitor on the other side is greater than minus Vsat. So the capacitor starts to discharge. So this is the path that it is following. Now what is the voltage at the non-inverting pin? I am going back and forth, but it is very simple. Now what is the voltage at the non-inverting pin? Earlier it was B times plus Vsat, now it will be B times minus Vsat. Okay. So while comparing, while this capacitor is going down, now your new reference is minus B Vsat. So as long as your capacitor voltage is above minus Vsat, the output continues to be at minus Vsat. The moment the capacitor is discharging below this point, the input at the non-inverting pin is now larger. Even though it is negative, it is still larger, right? See here, this capacitor voltage is going down, but this is a reference. So the voltage at non-inverting pin becomes larger. Means what? The output again switches back to plus Vsat. Once the output switches back to Vsat, the capacitor again starts charging. So this continuous cycle of charging and discharging happens. Thereby we get at the output a voltage waveform which switches between plus Vsat to minus Vsat. So this is a circuit of a relaxation oscillator, where now the time period is given by a certain expression. We are not going to do the derivation, you can just note down this expression. This time period t here, okay, it is given by the expression 2RC ln, which is as in natural ln, okay, 1 plus B upon 1 minus B, where what is B? B is your voltage divider network, which is R1 divided by R1 plus R2. So for a op-amp relaxation oscillator, the time period is given by 2 RC times ln 1 plus B divided by 1 minus B. Now let us try to solve a numerical based on this particular circuit. So let's go back to this board and try to see a relaxation oscillator and see what the values of the time period are, or in other words, what is the frequency of this oscillator that we are now going to design. The circuit given is the same. Okay. The only parameters that are given are the parameters for R are given and the parameters for C are given. The value of R is 10K, okay, and the value of C is 0.01 microfarad. Okay. The question that they have asked is, you need to find out what is the frequency. They are not asking what's the time period. You know the equation for time period, right? So the equation for time period was T is equal to 2 RC ln 1 plus B by 1 minus B. Okay. So R is given, C is given. Can I find out B? What is B? Of course, B is nothing but your R1 divided by R1 plus R2. Okay. And the values of R1 and R2 are also given in the circuit. The value of R1 is known to be 47 kilo ohm and the value of R2 is given to be 10 kilo ohm. Okay. So by simply substituting all these values of R, C and the value of B, we can get the time period T. So the time period T is then given by, if you can just substitute all these values, we are going to get it as 469 microseconds. Okay, what is time period now? This is nothing but, this is your output waveform going between plus Vsat to minus Vsat. It is always fluctuating between plus and minus, and this becomes your time period T, right? So now that the time period is known, can I calculate what is the frequency, right? So frequency is nothing but your reciprocal of the time period. So F is nothing but 1 upon T. So if you do the math here, the simple math, we are going to get the answer as 2.13 kilohertz. 2.13 kilohertz. Now the question that has been asked is to find the frequency, plus they have also asked you to find out what is the peak to peak value for the output waveform. So what's the output waveform? This is the output waveform that I am saying. When I mean peak to peak, it is going from plus Vsat to minus Vsat, means what? There must be 0 somewhere here, right? So the 0 is somewhere here. So this becomes its positive peak and this becomes its negative peak. So your peak to peak is nothing but the difference between this point and this point. So what is V peak to peak then? Your V peak to peak is nothing but Vsat minus this value minus this value, right? And what is this value now? Minus Vsat. So Vsat minus of minus Vsat, it becomes Vsat plus Vsat. So your peak to peak is nothing but 2 times the saturation voltage of this op amp. The saturation voltage of this op amp is given as 12.5 volts, okay, which is usually less than the supply voltage. Typically, if your supply voltage is plus 15, then your saturation voltage or V plus would be plus 12.5. Okay. So saturation voltage is given as plus 12.5. So 2 times that, it becomes your 25 volts. So in this example, what we have seen is we could calculate the time period, hence find the frequency, and then draw the waveform, analyze that and find the peak to peak, which happens to be 2 times the saturation voltage, which is nothing but your 25 volts. So this would be the numerical that we are looking at, which sort of enhances the concepts that we have learned for the relaxation oscillator. So let's move on then and try to see the last application that we are looking at for this op amp. So far what we have studied is nothing but a linear amplifier, right? What does linear amplifier mean? Suppose let us say I have a frequencies in the range 0 to f1. If I have a gain of A1 at 0 frequency, then I continue to have the gain of A1 up to F1. That means what? It will amplify all those signals with uniform gain. That is what is called as linearity. Now essentially all the circuits that we want to use would have to be linear, right? Like let us say I am speaking now, right? So this is a speech signal or an audio signal, it has a certain band. Now whenever I am amplifying this my voice over here, you increase the volume knob in your laptop or in your PC or in your audio player, you would like all these frequency ranges to be amplified to the equal amount. Rather than trying to use what you call as a graphic equalizer. What does a graphic equalizer have? You only go and amplify certain frequencies, or you can suppress certain frequencies. But if I want to amplify my entire voice signal, I have to amplify all these with the same gain. But there are some applications, very surprisingly, you may believe or not, you may require non-linearity, in the sense I want to amplify different frequencies with different gains. Wow, so that's a good example to have. So that circuit is shown here. Now what does this circuit do? This circuit is nothing but an inverting amplifier circuit, right? You are connecting the input to the inverting pin. You are having an RC network, so typically it's a high pass amplifier that we are looking at. It suppresses the low frequencies, okay, only the high frequencies are passed. But even in these high frequencies, I would like to amplify only those signals which are small. I'll just draw a waveform here. My input, it can be either a small input like this with a peak to peak as very less, or it can be another signal which is a larger one. Let us say both are of the same frequency. Since it's a high pass filter, now the frequency is the same. The red curve also has the same frequency as the blue curve because both have the same time period. But I would only like to push the red curve and I would like to suppress the blue curve. This is called as a non-linearity, right? Same frequency, two signals, but send one, suppress other. How is it possible? It is possible if you look at what are their amplitudes. So the red one has a smaller amplitude, whereas the blue one has a larger amplitude. In this case, for the time being, let us ignore the diode part of it, right? So let us say if my signal is very small, right? If my signal is very small, it can neither forward bias D2 nor can it forward bias D1. For positive values of Vi, when I am doing the red signal, is small enough to make this on, small enough negative values, small enough to make D1 on. So both D1 and D2 cannot be on, in the sense the signal passes through the op amp and I can amplify that. The moment your signal becomes large, which happens the case with a blue waveform here, the moment it is large, okay, I'll go back and let's redo it once again. The moment the signal is large, what happens? These two diodes turn on. For a positive value, D2 turns on. For negative values, D1 turns on. So for a large signal, okay, both the diodes turn on. Means what? I am bypassing the op amp. I am not amplifying through the op amp. Only those signals which are small are getting amplified, but the larger amplitudes are suppressed. So I can sort of suppress this large signal and only send the small signal. So this is what is called as a non-linear amplifier, which is typically used to suppress the noise which can be required for calibrating a millivoltmeter, which is shown here. So far then in this entire thing, we have seen many applications, starting from a simple case of a peak detector to all other amplifiers. So let us now then rewind and see what is it that we have done in this entire session. We have basically done some more applications of operational amplifier. Now with that, we would come to the close of this entire module. Session of course done and the entire module. So let us quickly go back and look what is it that we have done in this module. In this entire module, which spanned around 7 sessions, so you can say, we started with FETs, okay, the field effect transistors, we did JFETs, the junction field effect transistors, and then we did MOSFETs, the metal oxide semiconductor FETs. We compared between the BJTs and FETs to start with, and then we also compared the the JFETs with MOSFETs. We then went on to see how we can bias these MOSFETs, okay, especially the JFETs that we have done, okay, biasing the FETs basically. And then we saw many applications for FETs, and then we studied a very interesting circuit called as a CMOS inverter, which has both NMOS devices and PMOS devices, which is N-channel MOS and P-channel MOS. That's a very interesting circuit. It had almost zero power dissipation and very good at suppressing the noise. So that's the basis of most of the digital circuits that we're using nowadays in VLSI. And then we saw the wave shaping circuits using only ICs. Essentially, we studied what is called as a stable multivibrator, and we studied what is called as a monostable multivibrator. We also saw some numericals for biasing and these multivibrators. In the last leg of this particular module, we studied the op-amp, its behavior, its parameters, compared with the ideal and practical, and then we saw many applications where op-amp could be used. So I hope with this will be a good kickstart for this entire course. If you have any doubts, you can get back, try to use the reference books which are provided there, and try to solve more and more numericals which will enhance your concepts. Believe me, it's only while doing the numericals will you start questioning yourself. If you're trying to answer a theoretical question like what is an op-amp or what is an application as a peak detector or application as a filter, unless and until you start writing those equations, like unless and until you start asking what is 6 decibel per octave, what is 20 decibel per decade, you will not be enhancing your concepts. So I urge you to solve more such problems, thereby you can enhance the concepts that you have learned. So that's it from my side. Thank you.